All right, so let's continue. I'm sorry for being very pushy today, but I would like to leave a bit earlier, and maybe you also have a longer lunch break. So, okay, so what is the, like a takeaway? What's the takeaway for all this, our first half? So why we can find the short paths in the sort of without the global view? Because first we have this globally agreed ID space. So we need to map it, and we need to agree that this is how every player in the world agrees that this is my ID, this is your ID, and also we have to know the distance function that we also agree. And once we have it, then if we have say this implicit existence of underlying lattice, so either explicitly that you actually form a ring, or implicitly that it appears through enough long-range links, then this underlying lattice, if nothing else, it allows us to assure that the message will eventually converge. Maybe slowly, but will converge. So if you have a ring, you can always go to any place or another place just by greedily routing. And if you have these Kleinbergian long-range links, we know that we will progress to the target very rapidly, and at every point will be efficient. At every step, we will be able to logarithmically halve the distance. And even though these guys measured this sort of in this paper, like that, this seems to be how the bloggers connect, and there are other papers that show that the real world works that way. We are not really sure why we connect. I mean, what is the underlying processes that force us to do that? Because remember, I even showed you how to calculate the probabilities to do that artificially, if you say create a peer-to-peer system. But why we somehow in our everyday life, and not only social graphs but also protein networks and so on, also operate on that phenomena, it's not exactly clear yet. So maybe you will do PhD and figure out why, and then get some big prizes. So okay, with this I sort of will finish the models part. Okay, so I'll just want to re-emphasize that when we look at the network, of course we can look at everything microscopically, how if the Peter has 55 friends and these 55 friends have that many friends themselves, that's one thing. But most what you want to do is look at the macroscopic properties, not about specific Peter or John or Sandra, but overall how the social network looks like, what are the basic, the parameters, what is the phenomena that drives this network. So basically we looked at these main things: diameter, clustering coefficient, degree distribution, largest components, navigability. So that's what I sort of invite you to look at the systems and the networks and the graphs from the macroscopic perspective. And we covered these network models that hopefully sort of give you insight in how real world works. And of course we went from the simplest to the most complicated. And don't neglect the simplest. They can serve us as a baseline to compare and to see whether things we see has a underlying phenomena, just pure things at random. Good. So maybe before I continue, let's do a quick Kahoot. Can you log into your that we sort of remind ourselves. I'm sorry, I don't have a prize for today, but I promise for the next Kahoot I will bring something. So this is just for fame. Oh, we have even a sound today. That's very interesting. All right, please join. I think this time will be easier, Kahoot. So now, in order to become a winner, you have to also be quick. Oh, I didn't know you can actually have Instead of names, you can have emojis. Okay, we have a cake and a whale. Very nice. Everyone is in? Shall I start? Everyone is in, right? Okay. 5 questions. Node clustering coefficient is when we have k a node degree and n is the size of the network. Zero. Ooh, okay. I was hoping to do a better job with explaining clustering coefficient. Okay, let's see what was wrong. So if k is a node degree, if we divide node degree by n, so first of all, clustering coefficient is actually, in a sense, what we discussed, number of triangles in our vicinity, right? And then you would like to see how the formula is, you see how many friendships exist among your friends, and you normalize it or divide by all possible friendships among your friends. And that was maybe a bit tricky, because that could be somehow, you know, it looked like similar. I see that this got the most votes. But in that case, k should have been not your degree, but the number of edges you see among your friends. And n should have been not the overall network size, but the number, actually your degree, because you would calculate all possible pairs between your neighbors. So this is not the correct answer, and the correct answer is this, because it actually defines a probability that any 2 neighbors are connected. And this is not the case either. And then there is another one, is a probability that there exists a path between any 2 nodes. That's basically saying that there is a connected component, but nothing to do with the clustering coefficient. So I congratulate the 6 guys who did it right. The rest, please review your understanding of clustering coefficient. Let's continue. And we see Balind in the first place and the cake in the second. Very nice. Okay, degree distribution real networks usually exhibit. That should be easy. Four, 3, 2, 1, and we go. Okay, so at least the majority guessed it right. Remember, we were all the time talking that real-world networks, because one of the components on the construction is this rich gets richer, you will get this power law degree distribution where extreme events, although rare, they're likely. So we'll have some very rich nodes. Binomial would be for random walk networks. Remember, we discussed, and it's not exactly what you see in the real networks. Uniform distribution would be, you know, if everyone has a more or less the same. That's very hard to achieve, actually. You could have it, but that's, you know, peer-to-peer networks would probably have it, because then you try to impose that everyone has, you know, more or less constant degree distribution. And exponential, well, it looks like sometimes as a power law, but when we saw before, the extreme events are not likely there. So we don't see it in real world networks. But again, majority guessed well, so I am happy about that. Maybe I did a better job than in the first. And we have the same people on top. Let's do next. Sparse random graphs with the p more than 1 over n exhibit. Four, 3, 2, 1, and we go. Ooh. So okay, let's go. Random graphs, sparse random graphs, exhibit short diameter and large clustering coefficient. large clustering in random graphs is not the thing you want to find. We discussed that. The probability that any of your friends are connected is extremely low, especially when n goes to large numbers. And of course, if it is sparse, if it is dense, yeah, then you might have many triangles, but we don't talk about dense random, or in general about dense networks. We don't like to talk in this class. Then small clustering coefficient and power law degree distribution. This part is correct, but power law is not. We proved that random graphs have binomial degree distribution, so that's not good either. Then the green one, large diameter binomial degree distribution. So now the distribution is correct, but large diameter is not correct. We showed that if you have, on average more than one, you get a connected component, and your degree goes, your diameter goes down very fast. So the message is random graphs have low diameters. And then the remaining one is correct one large connected component. Remember, we discussed that the connected component appears very fast with a very few number of basically links, and that's what happens when p is more than 1/n. And small clustering coefficient. Of course, you have a small clustering in random graphs. So these, we have only 5 here. So again, please recap it, because all of these things will be asked in one way or the other in the exam. Maybe it will be more sophisticated sort of examples, and then I will have to ask you to argue this way or the other way. But in a sense, I will make sure you know the properties of the networks. Good. So let's see. Again, we don't, maybe it's got stuck the top rank. We have now correct statement. Oh, good, majority guessed, but the distribution is quite uniform. Okay, let's go over. Preferred attachment model can produce disconnected graph. Remember, we always connect, so it cannot get disconnected. So the thing is that we start with connected graph, and every node that comes connects to the component, so it cannot get disconnected. Configuration model can produce graphs with any degree sequence, and that's what we discussed. It's not always possible having arbitrary degree sequence to produce a graph. If you have a degree 10, 2, 2, you don't have sort of possibility. Or let's say, if nothing else, the number of the sort of the sum of the degrees should be the sum of the edge endings, or the degrees should be even number. Otherwise, one edge might not have even the ending. So this is not the case. And the preferential attachment might produce binomial degree distribution. So again, preferential attachment is Rijkstra per phenomena, and it will produce parallel degree distribution, not binomial. Binomial is the business for random graphs. And then what's left is configuration model might produce binomial degree distribution. So basically this is actually depends from where you start. If you start with such a degree sequence that is binomial, you will get binomial. So that's the only correct answer here. Okay, few more questions. Oh, we have the change in the Achilles is the first. Okay, let's see if the Achilles will continue being the first after this. Watson-Strogatz small world networks. Three, 2, 1, and we go. Okay. Good, so let's go. So Watson-Strogatz can explain Milgram small world experiment. Well, not exactly. As we saw, it can explain only that we have a network with low diameter, high clusterization, but we don't know how to route in that. And actually, what we showed, you cannot route efficiently decentralized manner in Watson-Strogat's network, and that's why it does not explain this experiment. Watson-Strogat enable efficient decentralized routing. That's the same thing in a sense. So it doesn't enable. It actually has a quite bad routing performance. Another one which does not get many votes. Watson-Strogat have many hub nodes. No, it doesn't, because you start with the everyone is equal, and when you rewire in the Erdős-Rényi process, basically you don't get this power law distribution where you have extreme rich or people. If you would do something with the rich gets richer, then it could produce it, but in our case it doesn't. And the remaining is a default one which says low diameter and large clusterization. That's basically the reason behind Watson-Strogat. Good, and then I think the last, oh no, that's the last. So, Achilles is the first, the cake is the second, and Spiro is the third. So congratulations, guys. I don't have what to give you, but next time. Good, so let's continue with the lecture then. Good, so this we already covered. Now, what I want now to talk, it's not a model, it's more the specific sort of type of graph that we can call expanders. And now expanders are such a beast that they are sparse, but very well connected. So meaning that it's very hard to, break them. So if you are an attacker and if you want to, isolate some sort of number of nodes in your network, and if you have scissors that can cut some links until they get blunt and you cannot cut anymore, you should not attack expanders, because you will have to cut a lot in order to isolate any reasonable number of nodes. So for example, tell me, do you think a ring would be a good expander? If you're an attacker, if you want to isolate, say, large fraction of these nodes, how many cuts do you need to make? 2, yeah. So basically, with 2 cuts, you can isolate even half of the nodes. So if your benefit is sort of measured by the number of people you isolate and the cost by the number of cuts, this is a very good deal, right? So basically, that would be the intuition. Can one isolate large number of nodes by removing small number of edges? And then you can define the expansion alpha on a graph G, where we say that given any subset S, we can now measure, and if the cardinality of this subset S is we call it NS, and then overall number of nodes is N, we measure how many cuts we need to make in order to isolate this subset, and we call it CS. And then expansion would be basically the minimal number of these cuts over all possible subsets. And then what we want also to normalize it by the number of people in that set that we basically cut. So the cut versus the number of people we isolate. And we have this strange thing which is minimal NS, and the N minus NS is such that we always take the smaller part of this. Either we take this guy, or the remaining guys, the complement, if this is too large. So we always see our cost is the minimal number of nodes out of the set we isolate. Okay, and then we go through all possible sets. And then we say that this ratio gives us the expansion of the network. And if this, and this in a sense measures how robust are our graphs. So normally, we say it's robust if you, basically the intuition is the following. To isolate k nodes, one needs to remove at least alpha times k edges. That would be the interpretation. Okay, so if you want to isolate k nodes, let's say this is the guys, you would need to remove this on expectation expansion number of edges. So tell me, oops, random graph, good expander. So imagine if you need to isolate I don't know, 10 guys in a random graph. And let's say on average you have 3 links per. Now compare it, say, with, okay, let's take 3. Is 3 a good expander? No, because there, you know, if you know where to cut next to the root, you will isolate almost half of the nodes with, you know, very one or a few cuts. Grid. Well, it's, you know, it's how to say, grid. You can isolate, say, if you have a if you cut, you know, k times 4, you'll isolate k square, right? So it's okay, but it's worse than with the 3. With 3, you just and random graph is actually the worst. Basically, it's a very good expander. You have to cut a lot to isolate because all of they go left and right. So in some sense, we can see that random graphs have very high expansion. A network which would have very clear clusters, let's say a tree or some other network where, you know, you have a, I don't know, a cluster for say butterfly lovers and the Ferrari lovers, and there are very few links in between, that will also be easy to separate. So social networks in some sense are not super good expanders. I mean, something is in between, but so the message is the following. Whenever you have a very clearly pronounced clusters, the expansion is bad, because clusters by definition means very little links going from one cluster to another. And if this is the case, the attacker could cut it off efficiently. Okay. And that now will depend for the future when we'll talk about convergence of random walks and graphs and how to calculate eigenvectors, is that in the networks which have very good expansion, things converge very quickly. Okay, you start, say, a random walk, and this process, you know, or let's say you spill some kind of a, I don't know, a water on a node and it goes through the pipes in the network. So if it is a good expander, it will reach very quickly in few number of hops everything. While if you do it in some social graph, it will maybe very quickly reach the boundaries of your cluster, and then you'll have to propagate a bit slower to the other clusters, and it will take time to sort of to propagate across the network. So that would say it's not a very good expander. So basically, what we say, a graph is an expander if the number of edges originating from every subset of vertices is larger than the number of vertices at least by a constant factor. Basically, you would like to, you know, work, if it is a good expander, you have to work harder, you know, you have to cut at least, say, k nodes, k edges to isolate k nodes. If it is less, then maybe the attacker could do it very efficiently. So, okay, so what we say is that these graphs are sparse yet very well connected. And now we started going to the spectral graph theory. And again, I will not give proofs. The proofs actually I posted you in Canvas from my other course, where I discuss in very detail why it is and how to interpret it, you know, point by point. But here I just give you the facts. So I will not bother you with why it works, but it's quite cool. The eigenvalues of this, if you take a adjacency matrix represented that graph, the small second eigenvalue of a random walk matrix would indicate that the graph is a very good expander. And basically, that's what we're most interested at, how random walk converges. So we say that random walk, or the processes that go on this graph, will converge very quickly for the expanders. And then another thing that we could use maybe in practice is that for expander graphs, if you have expander graph with sort of more or less fixed node degree, so say like peer-to-peer networks, random walk of very short TTL, say only of log n, would give a uniform random sample from the whole population, meaning that you'd be able to go to whichever node you like with equal probability, meaning that your random walk converged in a very few number of steps. So with this, I would like now to start a new sort of this part of the course, which is really to discuss how to interpret these random walks and how we can use it for our advantage. So we'll later see whether, for example, we can cluster the graphs, and if nothing else, how to extract the best centralities we know. And probably you already have in mind, page rank. So you'll see the page rank towards the end of this part. So let's start with something easy. So basically, random walk is just nothing else that you start from a specific node and then you go to any of the neighbors with equal probability depending on how many neighbors you have. So basically we move to neighboring node probability 1 over the d of the node v, where d of node v is the degree of the network. Okay, so it's very easy. And basically this sequence is we call it a Markov chain. So basically it does not, whenever you hear the word Markov, it does not depend on the history, it just depends on where you are at the moment. So okay, now tell me, if we have now such a graph, and we now tell at time 0 the probability that the message is in node 1 is 1, so basically we have message here or a walker here, and in the rest we don't have anything, so probability is that it's in time 0 at this node is 0. Now tell me, at time 1, what will be the probabilities here that we see the walker? What will be at time, next time step here, what's the probability here for node 1? Sorry? 0, for sure, because a random walk implies that you have to go somewhere. You cannot stay, unless there is a self loop, but we don't have self loop here, so it will be 0. Here what will be? 50%, because this is the, you go either here with half, so it would be 50, 50, 0, 0. Okay, let's try, what's now here? What would be here the probability now in the further next step? Sorry?
50%.
Are you sure?
Yeah, like if we start from now 2, we can go either to 1 or 4. So
yeah, but we are here only with probability 50.
okay, so it's...
Because now we have to see, if we started at time 1 here for sure, what would be the probability that at time 2 we are here? 40%. So with we came here with the half probability, and then with we have to multiply another half to go here or here, right? And if we're at here, what will be the probability? Will go to 5. So here it is half, and then times 1 over 3rd, right? So the probabilities would be the following. So basically at the second time step, for sure will not be neither a 2 nor a 3. For sure not, because we had to leave it. So it will be either we will come back to 1, and we could have come back to 1 either from 2 or from 3. So we had to basically calculate half times half plus half times a 3rd, right? And that will give us this number. The 5th node we will reach only through 3, so it will be half times a 3rd. And then to 4th we could have gone from both sides, so it's similar how this would be symmetric to 1, so it will be the same. And the whole would sum up to 1, right? So we don't lose any probability, right? So, and then we can continue like this. So we can see that at every time point we know we have different probabilities to reach something somewhere. So tell me what happens when I go to the very end. What do you think is here? Or after 1,000 steps.
One node is going to be 1, and the other 0.
It's proportional to the degrees of the nodes.
That was a good guess, but the wrong guess. And it could be in certain graphs. I mean, in certain graphs, and we'll see a bit later, it's usually directed graphs that would, for example, if you have a directed something to a hub, and if you go from everywhere, you try going, but you always go to the same place, you might end up only there, or can be trapped. But this is not really the case in connected graphs. There could be another issue. For example, if you have bipartite graphs, you might oscillate. You, at one time step, you're on the left somewhere, and there's 0 here, and next time step, you're on the right, and it's 0 there. And you always go. But for certain graphs, and we'll discuss a bit later, the rule is that, first of all, you will, at some point, keep on seeing the same lines. So that's one thing. That means you converge. So the random walk reaches stationary distribution. And another observation is, that's what your friend just said, the stationary distribution will not be just some kind of a random numbers. These random numbers will be proportional to the degree of the node. So if you now continue this thing, something happens. Now it's still not converged, so it's the 10 is not the same as 11 and 11 not the same as 12. But if we do it further, at some point we realize that the things got the same. So 29th row is the same as 30th row. Okay? And what we should know, that for any connected, so of course connected means that the random walk has to have a chance to go, so otherwise not even have a chance to go. And non-bipartite, meaning there's no oscillation, because bipartite would imply not convergence. You keep on going left and right and nothing sort of converges. But if it is connected non-bipartite bidirectional, sort of not directed graph, and you have any starting point, you can start wherever you want, random walk will converge. And it converges to, again, so not only it will converge to unique distribution. So not like once in this, another time in another one, no, to unique distribution. And this distribution, as we'll see later, will be proportional for every node depending on the degree. Okay, so the richer you are in the degree, the more chance the random walk will sort of converge there eventually than the poorer you are. And you can actually calculate it in several ways. One, will see that you can extract the principal eigenvector, or you just do the power iteration, which is exactly what we did, which is keep on multiplying. And we'll now see how we can do it with the matrices. But before, let's now just figure out what your just friend said. If it is really true that if our distribution will actually be proportional to the degree of every node. So let's put it that way, because now we observe that at time, n, this distribution pi is this, and at time pi prime, the next step is still the same. So now let's assume, let's now give it a shot, that this a cell here, a pi of v, of node v, would be actually proportional to the degree, so therefore d of v normalized by 2m, which is the number of edges. Okay, so let's see what happens. Okay, now we have our graph, and now let's do like the following. So let's calculate what happens at time, what happens with this vector at time, say pi prime on a node v. And let's say node v, let's say the node 3. Okay, so what, in order to figure out what is the value of this guy, we would need to go to every of the neighbor, see what are the values there, and multiply their values by the proportion, or let's say divide by the number of the links and sum them up, right? So we will sum up all the pi's that we see here of the neighbors of v. So we go through all the edges from v to u, you go to u, you see what's their value, and you sum them up by normalizing by the u's degree. It's a random walk, right? So now what happens next? So for example, this guy will take this value pi of this of the friend 4, divide by d over vi, that's how you say 3, and we'll sum it up to the final destination. Now we had assumption that this pi of u should be proportional to the degree, right? So we can now plug it in here. If we plug it this guy here, suddenly we can see that the degrees disappear, and we have now to sum up over all neighbors just 1 over the 2 of m. So we sum up how many times? Is that many times as we had neighbors. And that means we sum up d of v. I mean, that's how many neighbors we have. So what we see is that at the end, pi prime, if in a previous step pi had a value of dv over 2m that we plugged in here, the next step will be exactly the same, so that we will always be stuck in the same situation. Meaning that once you reached that every node has a value proportional to their degree, the next iteration would give the same value. Therefore, we converged. Is it good? Okay, I will leave you at home to figure out that this is correct, but at the moment, if you did not really follow me well, I just want to believe that random walk converges to unique distribution, and this distribution is defined by the proportionality of the degree. And here we show that if our previous time step is defined by the degree distribution, the next time step will be the same. Okay. So, and that's our implication. Basically, this means that it's proportional to the degree of v. And the intuition is that the more neighbors you have, the more chance you have to be visited, right? So this is now, and there will in the course in the fall we will even use it for many other things. And I think I also posted. You can see my classes in the on YouTube if you want to know more. But for now, let's now keep it as this, and now see how can we do it from a linear algebra perspective. So let's just remind ourselves what is adjacency matrix. Remember, we have a matrix. We can define any graph in adjacency matrix point of view, and this is the most default definition of a graph, where if we have a symmetric matrix of a size n, where n is number of nodes, where a cell ij has 0 if there is no link between node I and j, and there is 1 if there is a link between node I and j. Now we introduce a new matrix, which we'll call diagonal matrix. And by the name already implies that diagonal matrix has everything 0 except in the diagonal. And the diagonal will have values that are 1 over of the degree of that node. So for example, in our case, the first 1, 1 will be 1 over 2 because this guy had 2 links. And for example, the third and fourth node would have a 1 over 3 because they had 4 links. So now we have 2 matrices. Now let's go further. Now we'll define matrix M, which we'll call transition or random walk matrix. We'll simply multiply D times A. And that will give us, by intuition, a probability sort of matrix vector telling that what's the chance that the random walk from, say, row 1 or the node 1 would go to the node 2, to 3, to 4, to 5. So that's exactly what we sort of try to do in our thought experiment. Okay, so just be careful. Okay, well maybe so for bidirectional graphs they're all symmetric, but for directed graphs then it makes difference whether you talk from the one or the other perspective. And in some papers you might need to transpose it, because they define differently transition matrix, not from the row perspective, but from the column perspective. So just be careful. But in principle, nothing changes. You just would need to transpose it. Depends how you treat this vector, whether it's a column vector or the row vector. Yes?
In that directed case, you will need 2 diagonal matrices, because we have a different probability to move to a different node.
No, you will always need a diagonal. Diagonal matrix just says I'll need to normalize, sort of when I multiply by my links, I need to know by what to sort of weight to give the random walker probability to go. So you always need diagonal matrix.
But you will need, let's see. Since from one node to another, you have two nodes, and maybe you have a
so it's not symmetric. So it will not be symmetric.
But what about the diagonal? You would need
Diagonal is always symmetric. Diagonal just says what is the 1 over the degree of mine. It's always the same for any graph. But the random walk matrix would not be symmetric anymore for the directed graph. Okay, so now tell me the following. So in a sense, you can also interpret that A matrix A just gives us all one-hop paths. I mean, one hop is just neighbors, right? Now tell me, how can I get a matrix that gives me two-hop paths? Any ideas?
multiply again.
Yeah. So I just do A square. And now what does that mean? If I have a, and if I multiply by itself, so again from linear algebra point of view, I will get a new matrix. And now what this matrix would mean? So a cell ij in that new matrix, or A square matrix, would be basically a dot product of I row and j column. Okay. Now what does it mean dot product? That means we will take, you know, element here times element there, plus and then we will now, if we're unlucky, maybe it will be 0. But if it will be not 0, that means, what that means? That means there was at least somewhere in some, say, k position, a 1 in this row, where it's from that from I to in a cell ik, and also there was 1 from k to j, in order to be here 1, right? And if there is here 2, that means there was some other, you know, k2 place here and k2 place here, they also had 1s. Okay? And now, what does that mean? That means here that there was a link from I to k, and what it means here, that means that there was a link from k to j. So if I see here 1, that means there was 2 hop paths from I to j through some k. And if I see here 2, that means there were 2 paths from I to j, one from k, another from same k2. And the number I see here, I can know how many paths there are from I to j in 2 hops. This is clear. So basically, the A square just gives us a very quick view how many 2-hop paths there exist from I to j. So what would give us A cube? 3-hop paths. Okay, so that's easy. And okay, it's technically it's maybe not a path but a walk, but I mean, you know, you get the idea. So now, so if we take now a vector, like we said before, and we say that we represent a message. So say it's at the first node, and if we multiply it by A, what happens then? It indicates how many walks of length 1 this message can end up in node I. And that would mean that if we do VA, you will get a 0, 1, 1, 0, 0. That means this message could be in the second or the third the node with only one walk. And then you can do it V to the A square, and then you'll see that this message cannot appear in the second and third, but could appear at the fourth in 2 ways, and at the fifth in only 1 way. And that's exactly based on our initial graph. And you can do it as much as you like. Now, this will now multiplied by a adjacency matrix. What if we start multiplying by a random walk matrix? So if we take the same thing and multiply by a random walk matrix, we will get now probability that this message appears at any node in this vector. And that's exactly what we calculated in this table here. In the previous slides. And then if we do it again, now we'll you will do it, this was in the second time step, this is a third time step. And if we keep on doing that, what we now discussed before, we should reach a point where at some point the vector would produce the same vector. So that means if we start with some initial vector, and we'll have to start with the sort of probabilistic, the vector that sums up to 1, or so it's 1, 0, 0, 0, or any other distribution that is sums up to 1, and we multiply by random matrix m times, we get the, say, pt vector that represents the probability that our message will be at any of the nodes in this P. And again, this could be rewritten in a bit different way with the M transpose if you have column vectors, but that's just that you take care. So sometimes you see it vector times M if a vector is a row vector, or M times the matrix and vector if there's a column vector, and then you need to transpose the matrix. But that's the not important in the sense to understand the idea. But what is important is that we know that at some point we will have vector p in time t plus 1 will be equal to the previous time, and we can call this vector pi. And we also know that then that we can write it that way, that if you multiply pi by the random walk matrix, it will spit out the same pi vector. And this vector, since we have it of a say probabilistic vector, it will always be of the same length. So we don't even need to normalize anything. Okay, so in some sense what we just did, we found a dominant eigenvector of the transition matrix M, where the lambda is equal 1 basically. And I promised I'll send you home earlier. So with this I will finish, and we'll later figure out what exactly it means and what are the consequences for us while calculating the centralities and the web graph and clusterization and so on. So I thank you for your patience. Have a good weekend, and I see you, I think, on Wednesday at the same place, at the same time.